All right, let's talk about an unsung hero of the modern world. It's this massive piece of engineering that's running 24/7, pretty much hidden in plain sight at every oil refinery. It's called fluid catalytic cracking, or FCC, and it is, no joke, an absolute masterpiece of design.
So let's just start with a really simple question. Every car, every plane, they all need high quality fuel, right? But crude oil doesn't just come out of the ground ready to go. After the first round of refining, you're left with this thick, heavy, gunky sludge. So, how on earth do you turn that into something valuable? Well, the answer is a process of pure engineering genius. Okay, so our story really begins with this fundamental problem, a challenge that every single oil refinery on the planet has to deal with. And that problem is this stuff: heavy vacuum gas oil, or HVGO for short. After they've refined crude oil and pulled out the easy-to-get products, this is what's left over. Think of it as the dregs. Its molecules are really long and heavy, which makes it a pretty low-value byproduct. So the billion-dollar question for engineers was, how can we crack these long, heavy molecules into smaller, lighter, and way more valuable ones? The solution they came up with is, honestly, nothing short of magic. It's all built on two incredibly clever principles that act like superpowers: a very special catalyst and a mind-bending process called fluidization. So first up, the catalyst. You can think of a catalyst as a kind of chemical matchmaker. It's a substance that dramatically speeds up a chemical reaction. But, and this is key, it doesn't actually get used up in the process. For FCC, this isn't some liquid or a solid brick. It's an incredibly fine powder with particles about the same width as a human hair. This powder is the absolute key to breaking apart those heavy oil molecules. Now, the second superpower, this is where things get really, really cool: fluidization. This is the brilliant idea at the very heart of the whole process. Engineers figured out that if you blow gas up through that fine catalyst powder at just the right speed, the powder stops acting like a solid. It kind of lifts up, the particles separate, and the whole thing starts to flow and splash just like it's a liquid. And this is why fluidization is such a game changer. I mean, think about it. A static pile of powder? It's terrible for a chemical reaction. You get poor contact, uneven heat. It's just inefficient. But when you fluidize it, it flows like water. The heat is distributed perfectly, and every single particle of that catalyst makes maximum contact with the oil vapor. It's the secret to making this whole thing work on an industrial scale. So, with those two principles in mind, let's actually take a journey inside the heart of an FCC unit, starting with a component called the riser. This is basically our roadmap for the process. We're going to start right at the beginning with step one, the reaction itself. First, that heavy oil, the HVGO, gets heated up in a furnace to around 350 degrees Celsius. That's over 650 Fahrenheit, just to get it ready. Then it's injected right into the base of this really tall pipe called the riser. And this is where the action happens. As soon as that preheated oil enters the riser, it slams into a flowing stream of that fluidized catalyst, which is scorching hot. We're talking around 700 degrees Celsius. The intense heat instantly vaporizes the oil, and the cracking reaction begins in a fraction of a second. And when I say instantly, I really mean it. The entire journey up this massive pipe, where all the heavy molecules are getting shattered into lighter ones like gasoline, takes just 2 seconds. Any longer, and you'd start making stuff you don't want. That speed is precise, it's controlled, and it is absolutely critical to the whole process. Okay, reaction's done, got our valuable light hydrocarbon vapors, but now they're all mixed up with billions of these tiny solid catalyst particles. So the next big challenge is, how do you separate them? And you have to do it fast. So back to our map, we are now at steps 2 and 3. Separation and stripping. This whole mixture of hot vapor and catalyst powder shoots out of the top of the riser and into this enormous vessel that we call the reactor. Inside this giant vessel are these amazing devices called cyclones. And they do exactly what you think. They spin the mixture at incredible speeds. And then simple physics just takes over, right? Centrifugal force. The heavier, solid catalyst particles get thrown to the outside walls, where they fall down to the bottom. Meanwhile, the much lighter hydrocarbon vapors stay right in the center and exit out the top, on their way to becoming the fuel we use. You know, it's moments like this where you just have to stop and appreciate the sheer level of design here. As one force put it, it's like a giant puzzle. Every detail is calculated. every single temperature, every pressure, every flow rate inside this incredibly hostile environment is perfectly engineered. It's this beautiful symphony of physics and chemistry all working together.
All right, now for what I think is the most ingenious part of the entire system. What happens to all that catalyst after it's been separated out? This is where the FCC unit reveals its true brilliance, a perfect, self-sustaining loop. So here's the deal. During that 2-second reaction, a thin layer of carbon, which engineers call coke, builds up on all the catalyst particles. And this coke basically deactivates the catalyst. It makes it totally useless. Now, you can't just throw this stuff away. It's super expensive. You have to find a way to clean it. And this brings us to step 4 on our map, regeneration. The used or spent catalyst flows from the reactor into a second giant vessel right next to it, called the regenerator. And its one and only job is to bring this catalyst back to life. So how do they do it? It's actually shockingly simple. Inside the regenerator, they blast in hot air. This causes the coke on the catalyst to just burn off in a very highly controlled combustion. And as that coke burns, it releases a tremendous amount of energy, heating the catalyst right back up to that perfect 700-degree reaction temperature. And here it is. This is the punchline. The burning coke doesn't just clean the catalyst. The heat that it generates is the exact amount of heat needed for the reaction happening back in the riser. The unit literally powers itself. It's a perfect, continuous, thermally balanced loop where the problem, the coke, becomes the solution. It's brilliant. So the catalyst is clean, it's hot, it's ready to go back to work and do it all over again. But what about those hydrocarbon vapors that we separated out a few steps ago? This is the final step in the journey. This is where we see the real payoff. Those hot vapors flow from the reactor into a massive distillation column called the main fractionator. And inside, they're cooled down and separated by their different boiling points into the final products we use every single day. That thick, heavy sludge has now been transformed primarily into high-value gasoline, diesel, and LPG. You know, when you put it all together, the fluidization, that crazy 2-second reaction, the cyclones, and that unbelievably elegant self-powering loop, you realize the FCC unit isn't just another piece of industrial equipment. It's a true masterpiece of engineering. It's a perfect fusion of thermodynamics, fluid dynamics, and chemistry. So the next time you fill up your car, maybe you'll think for a second about the incredible journey that fuel went on. A journey through a 700-degree reactor, spun through cyclones, all created inside this incredible machine. It really is an engineering marvel, hidden in plain sight.